All right, welcome back. So in the previous video, we discussed the two basic types of photodetectors, the photoconductive photodetectors and the photovoltaic photodetectors. So in this video, we would like to go forward. So we were talking about improving the current, the photocurrent that we produce in a photodetector. And one of the key parameters was to increase the width of the depletion region in a photovoltaic detector, or the detection region we want to increase. So we saw that if you take a simple photodetector, simple PN junction, we cannot really increase the width that much because of the inherent limitations. So one of the alternatives is to actually use what are known as PIN junctions, PIN photodiodes. Okay, so we have already studied this in the context of PN junctions. So if you use a PIN diode, so you have a P-type region and then N-type region, and then sandwiching between that you have a intrinsic region, right? What is the advantage of this structure vis-a-vis the simple PN junction? Well, we'll see that. So the widths are this much. These are the standard numbers. So let's say if you have a PIN junction and you applied some reverse bias, okay? So what would be the field in this system? So well, to analyze that, we have done it multiple times in our PN junction analysis. So let's say you have the X and then the rho, the charge density I want to plot. So you have a P-type region on the left. So I'll have it, when it's depleted, you have charge, space charge, which looks like this, right? And then you have the width of this, some width. And then after that, you have basically a balancing charge, positive charge, which is coming because the N-type semiconductor being depleted. So what you have is plus Q here and a minus Q here. And the separation between them now is going to be the width of the intrinsic region. Why is this useful? Well, if you have such a scenario, we have also computed the electric fields. And the electric field should look like, you should remember this. We have even done a nanohub exercise on this. So X, let's say this is electric field. We know that electric field is going to be, pointing in the minus X direction. So it has to be a negative field, and it will essentially show a sharp rays here, linear in the depletion region. But because there is no charge in the intrinsic region, it is neutral, right? By definition, it is basically N equal to P there, and there's nothing to deplete. There's no space charge in that region. So what you're going to get is a flat electric field. There is no change in the electric field in this region. And then there is going to be a linear variation again in the N-type region. So this is the type of electric field. And we have seen that this is electric field is definitely smaller than 10 power 4 volts per second that you see in a typical PN junction. This might be of the order of, maybe, I don't remember now, but 10 power 3, I think 1000 volt per centimeter is what we have seen, I think, for some 3 to 4 micrometer widths. Okay. So, but what we are essentially doing is we are creating this electric field which will make the carriers move in opposite directions. For example, if I have electron hole pairs which are produced right in the center here, EH, what happens? The electric field is in this direction, so holes will go in this direction and electrons will go in this direction. And this electric field so immediately separates the electron holes, and because of that, the recombination of electron hole pairs is less probable. That's why we like photovoltaic detectors, because the recombination is reduced. Still, of course, there is going to be some recombination. We cannot completely avoid it, but the probability is reduced because we are making the carriers drift in the opposite directions. All right. So now that is one advantage of a PN diode compared to even PN diode has it, but now the width is, in the PN junction case, the width was only, limited to the depletion widths, which is micrometers. Now, this width of the depletion, intrinsic region can be anything that I design with. I can choose a 4 micrometer depletion width. Okay, there's nothing that stops me from doing that. If I do this, then I can have more absorption. Now, for example, one of the ways to build a photodetector would be to choose a thin layer of P+. The reason we are making it P+ is we want it to actually connect to the external circuit, right? So we don't want resistances in the minimize resistances, okay? I'll say N plus and P plus to minimize resistance. When you connect to the external circuit, it's finally electrons that are flowing, right? So once they reach the end, we just want to quickly go into the external circuit. We don't want to have contact resistances. Okay, that's why we want to heavily dope the P and the N regions. And now if you have photon flux, let's say phi naught, which is incident on this, what will happen? We have discussed optical absorption already. So if you have this photon flux incident, as let's say there's not much of absorption in the P plus region. Okay, it's a very thin region. And so what you will see is that there is a gradual decay in the photon count. And this decay is because of absorption, right? The photons are getting absorbed, and that's why the number of photons is reducing. And how is this? This function phi of x is going to be equal to phi naught, which is my incident flux, times exponential minus alpha x. This is going to be my photon flux as a function of position, right? So now, what will be the current? In the previous case, we assumed that the electron holes are produced uniformly, but once you have a sufficiently long depletion or intrinsic region, it is not going to be true anymore. And that is why I said that in the the expression JL equal to Q times width plus LP and plus LM times the GL is an estimation. It's not really correct because we are ignoring the decay of the photons. Okay, so what will be the current? Well, in this case, we'll have to calculate by JL. Let's say this is simply going to be the charge times the number of photons, right? And the number of photons, or rather number of electrons produced, that is going to be proportional to the number of photons at a particular distance. So the total amount of current is going to be integration of 0 to the width GL times dx, right? Or rather, I should say, if you have GL is a rate, right? This is going to, at each location, it's going to produce slightly different number of photons because there's a decay in the photon flux. So this is going to be equal to Q times 0 to W alpha, which is absorption coefficient, times the flux at that point, okay, phi of x, okay, and dx. So this is going to be equal to Q0 to width alpha times, I can put phi naught again, phi naught exponential minus alpha x dx. And so this is going to be equal to Q times phi naught times, it's an integration, so 0 to W. When it is 0, it is going to be 1, exponential of 1. So 1, it's going to be turned out, it's going to be this exponential minus alpha W. Okay. So if you have a certain flux incident, let's say this is going to be 10 power 15 centimeters per centimeter square per second. Okay. So this will be the intercharge will be the current that you will experience. We'll measure in this. Okay. By the way, yeah, this is assuming that assuming no recombination, of course, which is an approximation. Okay. All right. So what will this be? What will this current be in a PI junction? Well, let's try to do a small problem for that. So this is again from the textbook, 14.6. So PIN diode is given to you silicon. It has an intrinsic region of width 20 microns. That's wonderful. You have larger amount of collection capability there. Photon flux is 10 power 17. Alpha is this much. So I mean, this is just plug and chug. There's no reason for me to actually do it. So the incident flux phi naught is going to be 10 power 17. I'm leaving the units. Rather, let me write it. Always remember, flux is going to be per centimeter square. Okay. The rate is going to be per centimeter cube. Okay. So the current JL, or rather, if you want to write GL, GL is going to be what? Alpha times the absorption, whatever is the absorption coefficient, which is now in this case 10 power 3 per centimeter, times the flux, which is going to be 10 power 17 centimeter square per second. So this is going to be 10 power 20 per centimeter cube per second. Okay. So similar number as what we have taken in the photovoltaic devices. Okay. So with that, what will be the current? So JL, right? JL is basically Q times phi naught times 1 minus exponential minus alpha times the width. Okay, this is going to be 1.6 into 10 power 19 minus 19 times 10 power 17 times 1 minus exponential alpha. Alpha is 10 power 3 per centimeter inverse times W. Width is 20 microns. Just please remember, you should always put it in centimeters. So 10 power minus 4 centimeters. Okay. So that will be the same thing. This bracket, this guy will be exponential minus 10 power 3, 10 power minus 4. So 10, so 2 exponential minus 2. Okay, 1 minus exponential minus 2 times this. So you will calculate it and you see what this is. Okay. I don't want to do it. Well, yeah. All right. Exponential minus 1 is 0.3. Well, no, 0.66 minus 2 will be, yeah, you determine that. Okay. Square of that. So I guess it should be 0.3 or so, 0.3, and so this is 0.6. Well, I mean, yeah, 10 power minus 2. So I think 1.6 into 10 power minus 2 into this should be somewhere between 0.3 something. Check it out, okay? All right, so this is going to be my amps per centimeter square current, okay? Again, this current is much more significant than the reverse saturation current. So the reason I'm pointing this out is, this is the light induced current, okay? But in my devices, it turns out that my background, is a dark current, without any light, right? That is J dark. That is going to be 10 power minus 12 amps per centimeter square. So this is good for us. Signal to noise ratio is going to be high. This is noise, right? Our current is basically without anything, you're getting this current. So that's noise. And this is my signal. So I like to have high, for my detectors, any detector for the matter, you like to have high SNR, we say, signal to noise ratio. You want to have larger signal and smaller ratio, smaller noise. All right. So this is one way of achieving higher SNR. Okay. So there is one more class of photodetectors that we have. We can actually further improve it. Now we can even get higher current. How do we get that? Well, it turns out that we can achieve that by what is known as an avalanche photodiode. Okay. So in this, we will try to exploit the avalanche multiplication process that we discussed. Okay. So before I do that, this is basically a structure for a junction, that PA and avalanche photodetector that you can make. Okay. This is what it's going to look like. You're going to have the basic, well, anode and cathode. When we say anode and cathode, this is called anode, and the N plus is called cathode for historical reasons. So you have these things, and then you actually have a top layer which has to be transparent, and we want it to actually transmit as much as possible. We are actually talking about silicon here, right? Silicon has a refractive index of 3.4, right? So if you directly shine light on silicon from air, it turns out that a lot of light will be reflected, and the reflection coefficient is 3.4 minus 1 by 3.4 plus 1. So how much is that? I'm not sure. It will be about 40% or so. Okay. So about 40 to 50% of light will be reflected, and rest of it is transmitted. And we don't like that. So that's why, we can do some techniques by which we can reduce the reflection, so that all of the photons that are incident are actually going into the photodiode. Okay. This is Fresnel equation. I assume that you might have studied somewhere. If not, you can just check it out. Okay. If you have an index, refractive index, two materials with refractive index N1, N2, the reflection coefficient is going to be N2 minus N1 divided by N2 plus N1. Okay. So I'm assuming light is incident from air on silicon. So roughly this is going to be the reflection coefficient. Okay. It's a different matter. That's why, just I'm trying to give you the justification for what is known as this anti-reflective layer. So we want it to have less reflection. Okay. So that's why we can design that. There is some technique we can, you will study it some other time. All right. So you have the anti-reflecting layer, and then below that you make this structure of, let's say N plus, P plus, and then some other regions in between. Now we have introduced another P region here. The reason we do that is, if you have an N plus region and a P region, you're going to have a large electric field. Okay, we design this structure and doping in such a way that we have large enough electric field. So the electric field, if you plot it in the vertical direction, it turns out that in the end you don't have much. Then there is a sharp electric field because of N plus P junction, and then there is some normal amount of electric field, and then finally it comes down here in the P type. So it will be designed in such a way that the electric field is in excess of the field necessary for impact ionization. Remember, what is impact ionization? We said that if you have a semiconductor and you make electrons, if electrons are moving in a field, they get kinetic energy. When they get kinetic energy, they will hit another electron, or it can actually create one more electron hole pair. So the electron can actually hit electron which is part of the covalent bond and actually make it free. So thereby generating one more electron hole pair, and that process can repeat. So first, if you have one single energetic electron, that can produce two electrons can produce 4 electrons, and so on, right? 8 electrons and so on. So this kind of multiplication factor we can actually calculate, and I mean there's a lot of careful design that we have to do. And if you study a purely optoelectronic devices course, you will actually go through all that. But for us, what is important is we want to have a large multiplication factor. What do I mean by this? Well, it just means that in the previous cases, for every photon, there is, if we would like to have one electron produced. But now, for every photon, one photon is now going to produce m into m electrons, or rather m electron hole pairs, which is a multiplication factor. Okay, so by just creating this large field region, I'm quickly increasing the number of electrons. Thereby, I'm increasing the current, right? So basically, yeah, that's it. Okay. So, well, I mean, I'm just giving a very, very qualitative description, but I hope that, it makes you appreciate the concepts that we learned. Those concepts are actually useful for designing. You can actually do a design of efficient photodetectors. Okay. You will have technology tools, which are computational tools, which will help you design all these structures, and we can do very accurate calculations. And that is one of the directions that is interesting for us. All right. So these are again, PIN diodes and avalanche photodiodes are another interesting class of photodetectors. And nowadays, we even have photodetectors which can actually detect single photon at the single photon level. Okay. So we have built and we call them as SPADs, single photon avalanche photodetector. Okay. SPAD. So these are photodetectors which are designed very, very carefully to actually detect single photons. And these can be very, very costly. For example, a single SPAD, we have in our lab, and that costs about $20,000 on the higher end. Okay. So even though these concepts are simple enough for us to understand, to actually make it is actually quite challenging. And it's very, very interesting part of technology. It's very unfortunate that we don't have people who are making those in India. But I hope that, with sufficient amount of high-level technical knowledge, we can do that. All right. Okay. So I'll stop this part of the discussion here. So finally, I'll record one more video where I'll talk about the metrics of a photodetector, and with that, I'll close the discussion. So thank you very much for your attention. I'll see you in the next video. Bye.